Hello, my name is Chinedi Jude. I'm a master's student at the School of Physics. This video is to present the concept of redshift and Hubble's law and their applications. First, we need to understand what a galaxy is before we talk about distances to galaxies and how to determine such distances. A galaxy is a system of stars, a collection of stars in their millions and billions. Okay, this is together with gas and dust, and they are held together by gravitational force. On the image, you can see Andromeda Galaxy, also known as M31. Our home galaxy, where we are, is known as the Milky Way Galaxy. There are different ways of determining cosmic distances or distance to galaxies. These different methods fall into different categories, which are often referred to as cosmic distance ladder. These methods include, or the techniques include, parallax, the use of standard candles, and gravitational lensing. One particular one that interests us is the redshift and Hubble's law. The theory of the expanding universe was developed by Edwin Hubble in 1929. He inferred that redshift is caused by the relative motion between objects, or the Doppler effect. So when an object recedes an observer, there is an observed increase in the wavelength and consequently a redshift. But when an object approaches an observer, there is an observed reduction or decrease in the wavelength and consequently a blue shift. Based on the observed redshift, Hubble established that almost every galaxy is moving away from us, and the further away a galaxy is, the greater his redshift, or its redshift rather. And this is seen in Hubble's law, which states that the velocity or the recessional velocity of these galaxies is proportional to their distances from us. Okay, and this again tells that the further away a galaxy is, the faster it is moving away from us. This is seen in the equation where V is equal to h times d, where V is the velocity or the recessional velocity of the galaxy, and d is the distance or the cosmic distance to the galaxy. H naught is the Hubble's constant. Here it's a video where you see which illustrates that for a galaxy moving away from us, you can see the light getting lengthening, the wavelength is lengthening, and the light is also turning red shifting. While it was closer, it was a lot more blue. So how do we determine redshift, Z? Okay, this relative difference between the observed and emitted wavelength is obtained using a method of spectroscopy. So light from a target source is observed by a telescope, and the light from that gets into the telescope bounces off a grating, just as what a prism would do. The grating splits the light into its constituent wavelengths, and this creates a spectrum or a particular pattern of wavelengths. This pattern is observed to have lines or missing lines, and these lines or these missing lines depends on the characteristic atomic constituents of the observed object. These characteristic spectral lines observed from the spectrum of observed objects is seen to be shifted, and this depends on the galaxies, different from every galaxy, and it depends on whether the galaxy is receding or is moving away from us. So it's either moving away or coming closer to us. So for objects moving away, we see that these lines are shifted to the red end, and for objects coming closer or approaching, it is seen that these characteristic lines are shifted to the blue end. Redshift itself is denoted by Z and is expressed by a factor that means the relative difference between the emitted and the observed wavelength from an object. Redshift can also be used to determine the distance or cosmic distance to galaxies using Hubble's law, where velocity, the linear relationship between velocity and distance. and this applies for redshifts up to 0.1. Scientists also believe that the observed redshift for very distant galaxies is due to, or mainly due to, the expansion of the universe. As the universe expands, the light traveling through the space also stretches, causing a stretching or increase in the wavelength, and consequently redshift. The farthest thing that humanity has ever seen is the galaxy JS Z140, with a redshift of 14.32 and a distance of 34 billion light years. This means that the light observed by James Webb Space Telescope coming from this galaxy has been traveling for over 13.5 billion years, all the way reaching to us.